Okay, we're going to be in chapter 6, section 1, right? We're back to our normal textbook. We're going to begin talking about a radian measure. Okay, so maybe we remember what a radian is from geometry. I know for sure it showed up when you guys started talking about circles, probably towards the end of the year. But the definition of a radian is the measure of a central angle theta that intercepts an arc S equal in length to the radius r of the circle, right? Might not make a lot of sense the way that was written, but let's explore this concept a little bit further, right? So I'm going to draw a circle on this little coordinate plane that you guys see here, right? So let me see if I can get this right. I was kind of battling with this just a moment ago, so let me see if I can get it this time. Okay, nice. Okay, I got a circle. Okay, so here is a circle, all right? And you guys know a lot of things about circles right now, all right? You guys know that from, like, let's say this point, if I were to go a full rotation all the way around, that's 360 degrees, right? You know that from here to the y-axis, right, it's 90 degrees. And then from here to here, we know that that's 180 degrees, right? So we've done a lot of work with this before in degrees, right? So we already did this in degrees. I know that a full rotation is 360 degrees. This kind of showed up. I would kind of draw circles, not really all the time in the previous chapter, but we're going to relate all of these angles in degrees to a circle. I'm going to say from this center to that edge is r, right? That is our radius of this circle. All right, and what a radian is you can take this shape right here, this one measure of a radius, and let's just say you took that shape, this shape right here, and you kind of bent it so that it fits along this the circumference of your circle, right? So it fits along this edge right here. Like, so this right here, right? This is a curved little piece. This is one radius, right? We have a radius that of this circle that we kind of fit along this. This is a radian. So that's what a radian is, right? So from here to here, this is 1 radian, right? So this angle theta, again, is 1 radian. And if you keep doing that, right? So if I take another radius and I kind of fit it along the circumference of the circle, right? Kind of back to back with that one. And I say that this is another angle of theta, right? And this is another radius. So right now I have 2 radians. All right, so that's 2 radians right there. All right, if I do that again, right, I take another little radius, then we get 3 radians, right? So from here, this is 3 radians now. All right, and then this little bit right here, right, I did that on purpose, right, is gonna equal 0.141592, and so on and so on and so on. And then you can see that half of this circle makes 3.141592, whatever, radians, right? So that means half of the circle is pi radians, right? And if you took that same pi radians and you went all the way around the other side, then you would end up with a total of 2 pi radians, right? So that is 2 pi radians, all right? And this is a full circle. I'm going to say full circle, all right? A full circle is 2 pi radians, all right? We can relate that little demonstration right here, right? So you're probably like, Mr. Saldana, why did you do that? That didn't make any sense. It relates to this formula right here, that our angle theta is equal to S, the intercepted arc, over R, the radius, right? So let's just say this little intercepted arc was exactly equal to 1 of my radii, right? So 1 of the radii. Then we get theta equals R, the radius, over R, and that's just 1. So that's this little bit right here. All right, let's just say that the intercepted arc is the entire circle. So this entire circle right here, let's say that this is the intercepted arc. Well, I know that a full circle has 360 degrees, but I also know that that red circle that I just drew covers the entire circumference of the circle. And how do we describe a circumference? Well, we know that that is 2 pi r. So if I have 2 pi r as the intercepted arc over r, then the r's cancel out, and then I get that a full rotation is 2 pi radians. All right, we can take this a little bit further, and I can say that in this little circle, if I know that this right here is 2 pi radians, and I also know that at 180 degrees, I have half of the 2 pi radians, which is going to give us pi radians. I know that at 90 degrees, this is going to be half of pi, which half of pi is just half of pi, right? It's just pi over 2, right? And if I do the same thing at 270 degrees, then we're going to end up, you guys can do the math to kind of confirm this, we're going to get 3 pi over 2. Sorry, I don't know why the 3 looks like that. 3 pi over 2. 3 pi over 2. All right. So a radian has a corresponding degree measure that you guys are more familiar with, right? So everything up until now you guys have done in degrees, right? You guys pretty much know everything, triangles, circles, everything that you guys have done is in degrees. Radians actually have a little bit more of a practical use because they directly relate an angle measurement with a circle itself as opposed to like some arbitrary degree measurement. When you get to like higher maths like calculus and even in pre-calculus, which a lot of you are going to take next year, a lot of things we do in terms of radians. And it's not that degrees aren't particularly useful, it's just that, well, it doesn't really have a direct correlation with the circle. If you think about it, 360 degrees is really just kind of a random number, right? We kind of can easily picture degrees, right? That's kind of why we use it. Like if you make like a 90-degree turn, we all can kind of visualize what that is, right? But I would never really say, oh, I'm going to make a pi over 2 radian turn, right? That doesn't really make any sense. But you're going to see in this lesson and for the rest of this chapter that radians have some uses, right? You actually can do some pretty cool stuff with them, all right? But I did a lot of talking this first slide. Let's move on to actual examples. All right, so I introduced chapter 5 of the other book with coterminal angles. We're going to do the same exact thing here in radians, right? So since you know that with coterminal angles, it was plus minus 360 degrees, with radians, it's going to be plus minus 2 pi, which we just established in the previous slide, that 2 pi radians is a full rotation of a circle. All right, so let's try something like this, right? Let's find a coterminal angle to 17 pi over 6, right? I'm going to subtract for this first one, and then for number 2, I'm going to add, right? So let's subtract 2 pi, all right? It's not going to be as straightforward as degrees because I'm sure you guys can see from here that you need a common denominator, all right? So I need to write this over 1 and then times 6, and then so you end up with 17 pi over 6 minus 12 pi over 6, which is going to get you 5 pi over 6, right? So that is one of our coterminal angles, all right? And we can do the exact same thing here. Since it's negative, I'm going to try to find a positive one, right? So let's add 2 pi. And once again, it's not going to be as simple as it was in degrees, right? We're going to need a common denominator. So I'm going to write this over 1 times 3, and then you get negative 4 pi over 3 plus 6 pi over 3. And then when you do this, negative 4 pi plus 6 pi is going to get you 2 pi over 3, right? And that is your measurement in radians of just another coterminal angle, right? So really not too bad, just you don't really do it in one step like we did with degrees. Degrees are pretty easy, right? But here you need to do a little bit extra with the common denominator. All right, so like I established a couple slides ago, you do have a corresponding radian measurement for every degree, right? I mentioned that 90 degrees is pi over 2, 180 degrees is pi, and so on and so on. But really, you can do this for any degree measurement, all right? If you are given an angle in degrees and you want to convert it to radians, you're going to take your angle measurement theta and multiply it by pi over 180. If you have a measurement in radians and you want to convert it to degrees, you're going to just do the opposite. So it's going to be 180 over pi. A lot of you have taken chemistry or will take chemistry. You can think of this a lot like a conversion factor, like when you're doing stoichiometry, right? And you're having to convert from moles to grams, grams to moles, and all that, right? Depending on where you put the gram or the mole, whether it's the top or the bottom, is going to change depending on what you're looking for, right? So you can think of that kind of similar to this. All right, so we're going to convert from degrees to radians or vice versa, right? So let's check out this first one. I have 135 degrees. How do I know it's in degrees? Because it has a degree symbol, right? And that's one thing that you can check for all of these. So a radian, right, that's something important that I forgot to mention, right? A radian doesn't have a unit. It's not going to be like an actual measurement that has like a set unit attached to it. A radian is just a radian. Degrees, however, you're going to know that something is in degrees when it has the degree symbol. That's why we were really getting on you guys a little bit ago for having your degree symbols. That's why we took points off on your quiz if you forgot it. So yeah, that's why it's super important, especially now, to just be a little bit more careful with that, right? If something's in degrees, you need to be specific, because if you don't, then we assume it's in radians. All right, so this is in degrees. So let's convert it to radians, and to convert it to radians, I'm going to multiply by whatever has the degrees on the bottom. Again, a lot of you in chemistry or have taken chemistry, right? Think of it like a mole to gram or gram to mole conversion, right? If we're trying to get rid of degrees, I'm going to put degrees on the bottom. So pi over 180 degrees, you can cross out your degrees, and then you end up with 135 pi over 180. All right, that part's easy. The challenging part is going to be simplifying this as much as you can. As you see more of these numbers, you're going to get used to simplifying really big fractions, right? These actually have a common factor of 45. So if you divide the top and the bottom by 45, then you would end up with 3 pi over 4. And that's your angle in radians. All right, let's try the same thing with the next one. All right, this is another one that's in degrees, so I'm going to multiply it by pi over 180. Degrees, right? I'm trying to cancel out degrees, so I'm going to put it on the bottom. And then we end up with 540 pi over 180, right? Sometimes it helps at first just to get rid of the zeros, right? Divide them both by 10, and then 54 over 18 seems a little bit simpler to divide, right? 54 divided by 18 should get you 3. So then this is equal to 3 pi, all right? 45, we can do the same thing. We know it's in degrees because of the symbol. So this is going to be pi over 180 degrees, and then you can cross these out, and then you get 45 pi over 180. And then again, these are going to have a common factor of 45, so this is going to get you pi over 4. All right. Let's try the same thing with this one, right? I kind of already told you guys what 90 degrees is, right? So this is pi over 180 degrees. You can cross those out. You get 90 pi over 180, which is just going to get you pi over 2. All right. And then now you look at something like number 7. This is in radians. All right. You don't want to assume it's in radians just because you see a pi. But you know for sure that it's in radians because it doesn't have a degree symbol, right? That's really the biggest thing. So I'm going to instead multiply by the other conversion factor, right? It's going to be 180 degrees over pi. And then you can cross out the pi's. And then 180 divided by 6 is going to get you 30. So then you end up with 5 times 30 degrees, which is 150 degrees. All right. And then 3 pi over 4, we can do the same thing. I don't see a degree symbol, so I know it's 180 degrees over pi. You can cross out the pi's, and then the 180 and the 4 are going to simplify to 45. And then 3 times 45 is going to get you 135. All right. With negative pi over 2, same exact thing. I don't see a degree symbol, so I'm going to do 180 degrees over pi. The pi's cancel out, and then 180 and 2 simplify to 90. So then we end up with negative 90 degrees. All right. Something just like 5, right? It doesn't have a degree symbol. So even though you don't see a pi, you also don't see a degree symbol, so you can't assume it's in degree. You can't assume it's in degrees. So I'm going to do 180 over pi. All right. Nothing cancels out here, so then you end up with just 5 times 180, which gets you 900 over pi degrees, right? Kind of a strange degree, but that's perfectly fine. All right, if that's what we got, then that's what we got, right? Same exact thing here. I don't see a degree symbol, so I know that this is in radians. So I'm going to do 180 degrees over pi, and then so we get 360 over pi degrees. Again, not a pretty angle, but it is what it is, right? We didn't do anything wrong. We used the correct conversion factor, so we know that this is the correct answer. All right, let me just box those up. All right, and that's it for that page. All right. The last little bit of this lesson is just an application of radians. All right, we use it when we want to determine the arc length or the sector area, right? So we have that arc length. We typically denote it S. We typically denote it S equals R theta or theta R. And then the area of a sector is going to be 1 over 2. Wait, hang on. See, sorry, that was confusing me. Read it as 1/2 R squared theta. All right, I thought the whole thing was on the bottom. No, it's 1/2 R squared theta. And the important thing here is that the theta has to be in radians. If it's in degrees, you need to convert it to radians. All right. So we have a circle has a radius of 18.2 centimeters. I want to find the arc length and the area of a sector with theta equals 3 pi over 8. Well, we really have everything we need now, right? I already know what the radius is, so that's our r. And we know what theta is, and it's already in radians, and you can tell because there's no degree symbol, all right? So I'm going to start with s equals r theta to find the arc length. So I'm going to say s equals 18.2 times theta, which is 3 pi over 8. And we don't want to really leave it like this. We're going to plug it into the calculator. And it doesn't say, but I'm going to round to maybe like 1 or 2 decimal places. All right, so when you plug this into the calculator, we get approximately 21.44. I'm just going to say 44 centimeters. All right. And that's our arc length. All right, we want to find now the sector area. I'm going to use area is 1/2 r squared theta. All right, so then the area is going to be 1/2 18.2 squared times theta, which is 3 pi over 8. All right, and then we know that the area, all right, again, plug this in your calculator. I'll probably do the same, like 2 decimal places. Times 3 times. Should get you about 195.12 square centimeters. All right, so it shouldn't be too bad. It's just plugging into the calculator. All right. Now this one, it's asking us for the same information, except it gives us that theta is in degrees. All right, so now I want to first convert it to radians, right? Because our formula only makes sense in radians. All right, so I'm going to say that this is 144 degrees times pi over 180. All right, and then simplify this as much as you can. Should get you 4 pi over 5. All right, so now I have that 4 pi over 5 as my angle in radians. So then I'm going to do s equals r theta. So this is going to be s equals 18.2 times 4 pi over 5. So then I'll do the same thing. I'll use like 2 decimal places. All right, and then we should get 457.42 centimeters. All right, shouldn't be too bad. And then I'll do the same thing with the sector area. So it should be 1/2 r squared theta. So then area is 1/2 18.2 squared times 4 pi over 5. And then so the area should be, give me 1 second, should be 416.25 square centimeters. Wait, hang on. That doesn't look right. Oh, sorry. Made a little mistake. In my calculator, I put 182 instead of 18.2. Sorry about that. Should be 45.74 centimeters. All right. My bad. But yeah, that's it for this lesson. Shouldn't really be too bad. I know I went kind of heavy explaining what a radian is, but hopefully that made the concepts a little bit easier, right? But shouldn't be too bad.